Good morning to all. I am Fabio Parisi from Polytechnic of Bari, and I present a contribution named Optimal Trajectory Planning for a Robotic Manipulator Palletizing Tasks. A robotic manipulator has to move a finite number of objects from a storage area to a delivery area configured as in figure. We want to compute the optimal sequence of actions for moving objects from the storage to the delivery area in order to minimize the length of the traveled paths. We propose in this work a time-indexed formulation of the problem, where the decision variables are the pickup and delivery operation in the discrete time instance in which the operation is scheduled. In the slide, the notation necessary for the mathematical formulation is presented. N is the number of the object to move from the starting to the ending position. Capital S is the set of objects in the storage area, where each object is represented by its center of mass in the geometrical space. Capital E is the set of possible ending position in the delivery area. Capital L is the set of lengths of the F levels. The IJ denotes the length of the possible trajectory performed by the end effector during a pickup and delivery operation. The other parameters and variables describe the generic position and configuration of the object. LLB denotes the first time interval in which the object can be positioned in the level W, while LUB denotes the last time interval in which the object can be positioned in the level W. Y is the time index, the decision variable of the problem. The aim is to find the sequence of the movements of the manipulator that minimize the length of the traveled paths. The object function can be defined as the sum of all distances traveled by the end effector, and this minimization is subjected to different constraints. The unitary robot's load capacity for each turn, and the imposition to fill the previous level before starting the next one. The fourth constraint imposes that each object has to be posed in only one final destination. The fifth constraint imposes that the robot picks one of the objects on the top of the columns, and this constraint is imposed by verifying that every previous object in the column has already been picked in one of the previous time intervals. The sixth constraint forces the decision variable to be binary. In order to solve the problem, a configuration is selected by choosing the parameters and variables introduced previously on the left part of the slide. To compute the elements of the distance matrix, each subtask trajectory is structured so that collisions are avoided. Each subtask trajectory is divided into straight movements by introducing fixed points. As an example, in the figure on the right, the example of a subtask from starting position 14 to ending position 4 is shown. The programming phase is performed by using the online approach directly on the work cell. The theoretical solution of the problem is tested in experimental setup involving a KUKA KR3 robot manipulator. The objects to move are 3D printed parallelepipeds with dimensions of 25 for 25 for 75 millimeters and a weight of 30 grams. In figure are shown the starting, the intermediate, and final phase respectively. The speed used for the movement is 0.5 meter per second. This research aims at formalizing the problem of task sequencing of a robotic manipulator that has to palletize objects from a specific storage area to a specific delivery area. The problem is modeled as an integer linear programming problem to minimize the length of the end effector traveled paths. The IELP problem solution is tested by controlling a KUKA KR3, a robotic manipulator. The results show that the proposed approach can be easily applied in real environments. Future work will focus on the generalization of the movement without using fixed points on the over the load columns to avoid collisions. Moreover, system for palletizing large number of tasks will be solved, and optimal solution will be compared with heuristic ones. Thank you for your attention.